Here we're going to talk a little bit about the red number 40 in Soda Lab for Chem 141. In this experiment, our goal is to determine the concentration of red number 40 in a soda. Red number 40 is the thing that makes it look red. Turns out, there is a property, a measured property, that scales with the relative concentration of red 40, and that is what is known as the absorbance. Absorbance is tied to, if I put light through a sample of a colored solution, how much of the light that gets sent through the sample is absorbed by the sample. As I increase the concentration of the colored substance in my solution, the absorbance of that solution will increase. And it's in fact linear. Both epsilon and B are constants. Epsilon is molar absorptivity, and it's a function of the structure of the molecule. And B is what is known as the path length, basically how thick the sample is that the light is passing through. For our purposes, epsilon and B will remain constant. So in that case, absorbance is a function of concentration. So if I make a graph of absorbance versus concentration, I will get a straight line. What we're going to do in this experiment is we're going to make solutions of known concentration of red 40 from a stock solution. Then we are going to measure the absorbance of each one of those solutions, plot them on a graph, and allow us to calculate we will obtain the slope and the y-intercept of that line. What that will allow us to do is then measure the absorbance of our soda sample. If we know what M and B are, our slope and our y-intercept, we can go from absorbance and calculate concentration. Those of you who are taking Chem 141, this is very similar to the sugar and soda lab. We did almost the same idea. To make our solutions of known concentration, we are going to dilute a solution of known concentration. We're going to call it our stock solution. We're going to know what the concentration of stock solution. You'll be given a large bottle of known concentration. And what we're going to do is we're going to selectively dilute it. So we're going to take some amount, some volume of that stock solution, and we are going to dilute it into a larger volume and add water. So for example, we might take 5 milliliters of our stock solution of known concentration and then dilute it to 10 milliliters. So if we increase the volume by adding water, we end up diluting the sample. We can calculate the concentration of that diluted sample relatively simply. We are going to be using a volumetric flask to make these diluted samples, so the volume of the dilute will be very easy and it'll be a constant most of the day. The concentration of the stock, we'll know, it's on the side of our bottle. So as long as we know the volume of our stock solution that we put into our dilution, we should be able to calculate the concentration of the diluted sample. This is the concentration of the diluted sample that will be on our x-axis in our graph. So we're making several solutions of different concentrations, the concentrations of those diluted samples. The problem is going to come in is that measuring the volume of the stock solution, measuring actual volume of a small amount, a varying amount, isn't very accurate because it involves our brain and judging where the line is. So instead of measuring the volume of the stock solution that we put into our 10 milliliter volumetric flask, we can measure its mass. Because we can measure mass of how much solution we put into our container, we can measure that very accurately by using an analytical balance. And as long as I know what the density is, I can convert the mass of that stock solution into the volume of that stock solution. So we're going to tweak our dilution formula into something a little bit more useful. I know what the volume of the diluted soda sample is, since I know I'm diluting it into a volumetric flask. So I'm going to know what that is, so probably 10.00 milliliters. So since I know that the volume of the stock solution is the mass of the stock solution divided by the density, just looking at the units tells me that, in my dilution formula, I needed the volume of the stock, but I'm not going to measure that. Instead, I'm going to measure the mass of the stock. I can measure that accurately. The density of the stock, I will also know. It's also on the side of my source ball. So we're going to rewrite our dilution formula here. So our concentration of stock is our constant, density is a constant, our volume of the dilute is constant. And so as our mass of stock changes for each dilution, again, this is a very accurate number, we can calculate the concentration of our diluted sample very accurately. So we'll have our red 40, our stock solution, and what we're going to do is we're going to make a series of dilutions. We're going to make several different dilutions, and we're going to know exactly how much stock solution we put in, diluted to, again, probably 10 milliliters. And with each of those solutions, we are going to measure the absorbance of each one of those dilutions. And that each one of those will give us 1 point along our what is referred to as a Beer's law graph. This is Beer's law, and it's measuring absorbance versus our diluted concentration. So we'll be able to get our graph, and we'll get our equation relating absorbance to concentration. Our soda sample, however, might be too dark. It turns out Beer's law only works if the solution is only a certain darkness. If it's too concentrated or too dark, the absorbance, this equation sort of like breaks down. So it only works if the concentrations are below a certain amount. And our concentration of red 40 is going to be too high. But that's okay, because we know how to dilute a sample. So we have our red number 40 from our soda sample, and what we're going to do is we're going to selectively dilute it. Like we're going to add a certain amount of our soda, and we're going to dilute it to 10 milliliters. We're going to do the same sort of dilution formula as we did before. We're going to know the volume of our stock solution in that calculation. So we're going to take our diluted soda sample. From our diluted soda sample, we take the absorbance of that diluted soda sample. The reason why we made the graph is because it correlates the absorbance of a solution with its concentration. If I know the absorbance of the diluted unknown, I plug it into my equation, my slope and my y-intercept, and that gives me the concentration of that diluted soda sample. So knowing after I've diluted it, take the absorbance, gives me the concentration. But this is the concentration of the unknown after it's been diluted. This is what we're shooting for. This is our goal. This is our purpose, is to determine what's the concentration of red 40 in our original undiluted soda sample. Well, here we know what the concentration of the diluted sample is. When we did the dilution, we knew how much of the soda sample we used and how much we diluted it to, so we know V sub stock, V sub S, if you will, and we know VD for volume of the diluted. And now we know the concentration of the diluted. So we know VS, we know VD, and we know the concentration of the diluted, allowing us to calculate the concentration of, in this case, we're kind of calculating the concentration of the stock soda sample, the undiluted soda sample. Good luck.